We'll continue with our discussion of compressible potential flow governing equations. In the previous video, we talked a little bit about the history of how high-speed aircraft were being developed between the time Wright brothers flew their aircraft and towards the end of the Second World War. We kind of walked very quickly through some of the landmarks and landmines along the way. Then we started developing the governing equation just for the outer flow. We made a lot of assumptions. We assumed it was inviscid, steady, adiabatic, reversible, and irrotational. So we ended up with this particular equation that is shown in here. It's highly nonlinear, and in 3D you get a similar looking equation. So if you multiply everything through by a squared in 2D, you get this equation. This was solved numerically only in 1971. That means it took almost, I would say, full 70, 80 years before it could be solved on computers, digital computers. Two scientists, Earl Merman, at the time he was at NASA Ames Research Center. He later on became chair of the department of MIT. And Julian Cole at UCLA, they came up with solving this equation, a highly simplified form of this equation for transonic flow in 1971. Just a couple of years later, Professor Jamieson, currently at Stanford, he was at the Courant Institute in New York. He developed solving this equation for thick airfoils. Then several years later, people like me came along. I was working at Lockheed, so I extended this to two-dimensional unsteady transonic flow and also three-dimensional unsteady transonic flow. So a lot happened in the late 70s, but in the early stages of the 20th century, this equation was a big roadblock. People didn't know what to do with it. So we are going to make it linear. So we are going to go back to our old assumptions that we did before. We are going to assume the flow is steady, inviscid, irrotational, isentropic. We have already made it. We are going to deal with subsonic flow or supersonic flow. Our theory cannot very well handle transonic flow. I will explain why it is as we develop the methodology. We are going to assume that the body is very, very thin. It's got a very, very mild camber. It's operating at low angle of attack so that it disturbs the flow very, very slightly. So this is called a small disturbance assumption. So the body is so thin, when you stick it in a flow, most of the flow is free stream. But near the body, it does get disturbed, but only by a small amount. So think of a very, very thin foil-like shape. You put it in the air. Yeah, the flow will deflect about the foil shape, follow the contour of the foil. But if the foil shape is not very curved, small curvature, then it's going to be very slight velocity changes. So this is what we assume. So what we are going to do is we are going to take our velocity potential phi as made of two contributions. One is a free stream component, v infinity times x. By the way, we are going to assume the free stream velocity is along the x-axis. So the body is rotated like in a wind tunnel for an angle of attack fx. So the free stream is from left to right along the tunnel direction. So it's along the x-axis. So we are going to replace this velocity potential by something called the disturbance potential. So this becomes our new unknown because free stream velocity is known. This is just a variable x in the x direction. So now if you take a u d phi dx, which is u, you get the free stream flow plus a small disturbance caused by the presence of the body. If you take d phi dy, this is the partial derivative of phi with respect to y, you get a disturbance velocity d phi dy. Now because these are small disturbances, they are small compared to v infinity. So mathematically we can say the ratio of the disturbance velocity to the free stream velocity is very much smaller than 1 both for in the x direction and also in the y direction. So if this is hundreds of meter per second in the denominator, the numerator will be like a tenths of meter per second. So it's like a 0.1. So 0.1 is small compared to 1. So if you have $1 in your pocket and also 10 cents in your pocket, you'll be more likely to give up the 10 cents. You'd want to keep the $1 because it's a higher order of magnitude. So we are going to do an order of magnitude analysis and throw out the terms that are very, very small. Especially if something is squared, let's say this is only 10%, 0.1. If you square this, it's even smaller, 0.01. So second order terms we will throw away for sure. First order terms, we will take a careful look at it before we discard it. Because once you throw away a term, it's gone. Once you have thrown away your dime, you're not going to get it back. How about the second derivatives? It's very easy. When you do the second derivative, this completely goes away. So the second derivative with respect to x is phi xx, y is phi yy, xy is phi xy. So going back to this equation, second derivatives are all replaced by the second derivative of the disturbance potential. Now we are going to work on these coefficients, and these coefficients one at a time. Okay, we will start with something like this and then see what happens. So let's take the middle term, which is 2uv phi xy, which is this term. The minus is there, we know, we have not forgotten about it. So let's look at the order of magnitude of this particular term. Then what we get is u is free stream velocity plus disturbance velocity. V is a disturbance velocity. Now this is d by dx of phi y. So I can take this phi y inside and I can take this 2, it'll become phi y squared. Then I can divide by v infinity squared and multiply by v infinity squared. Well, then nothing has changed, and then I have 1 plus phi x over v infinity is the non-dimensional form of this velocity. So I have taken one of the v infinity outside, so it became v infinity. I non-dimensionalized phi y by v infinity. Then I got a v infinity squared. Okay, so this term is small. So anything squared, remember this is like 0.1. When you square it, 0.01. The derivative we assume is a small. So we're going to throw away this term. So we are using an order of magnitude approach and are making some assumptions and discarding terms in our attempt to make these governing equations linear. Next, we have to deal with the a squared, u squared, a squared minus u squared, a squared minus v squared, and so forth. So we reach back way back in energy equation we developed in this course, but also in 2010. Enthalpy plus kinetic energy, this combination is called the stagnation enthalpy. Stagnation enthalpy is a constant. Now Cp is a specific heat at constant pressure. Cv is a specific heat at constant volume. From thermodynamics, we know that the difference is R, the ratio is gamma. So you could write Cv as Cp over gamma. Then if you keep Cp to one side and take everything that involves gamma to the other side, you get this expression. Then Cp times T is gamma RT divided by gamma minus 1. So this becomes a squared over gamma minus 1. This is the velocity squared. This is the free stream velocity. It's free stream speed of sound squared over gamma minus 1 free stream velocity squared. Why did we go to trouble of developing this equation? Because we have a squared minus u squared. So we need some expression for a squared. So that's why we have gone to this form. Now I need a squared, so I'm going to take everything to the other side and keep the a squared to one side. By the way, this is an exercise. In the exam, these are fair game. I may ask you, show that, prove that. Be sure to see if you can develop these things. Okay, it's extremely important that you learn how to manipulate simple algebraic equations like this to get the shown expression. Okay. There's no approximation needed, no linearization. It's just a massaging of the terms, representing Cp in terms of what we wrote here. Mach number is flow velocity squared, V infinity squared, divided by A infinity squared. That's the Mach number squared. Okay. So please practice this. You need to be ready for the second quiz. Now, I'm going to take A squared on one side, take everything to the other side. Then I'm going to subtract from the A squared U squared. So skipping a couple of algebraic steps, that A squared minus U squared is like this. This is still exact. Okay. Now U is free stream velocity plus disturbance velocity. Therefore U squared is that combination squared. So if you bring the free stream velocity squared outside, you'll get 1 plus disturbance velocity over V infinity, whole thing squared. Okay. So little u is V infinity plus Vx. I have divided through by V infinity, but kept it out here. That's all I have done. I already had a V infinity here, so I put it in here. V is Vy over V infinity squared. And then u is, again, V infinity squared, this stuff here. Okay. Now we see immediately that this is a second power of a small number. 0.1 squared is 0.01, so I'm going to just neglect it. When you expand this, I'm going to get a plus b squared is a squared plus b squared plus 2ab. B squared is a small number, so I'm going to neglect it. Again, when I expand it, a plus b squared is a small number, so I'm going to neglect it. So I'm going to keep everything else. So then this expression, notice the approximate sign. I have thrown away some stuff between here and here, so we get an expression like this. Now, if you take the speed of sound outside, you get a 1 minus m infinity squared minus this term here. Now, it's still this term is still present here, so we are not going to throw this away because it's a first order term. You may wonder, why don't I throw it away? It's a first order term, it's a small number, why can't I throw it away? We could normally throw it away in very low subsonic flow when Mach number is very much less than 1, so that this difference is very, very large. We can do it in supersonic flow when Mach number is very high, because this number is very large. But in transonic flow, Mach number is close to 1, so this is a small number, these two combination. This is a small number, so we have to keep the entire enchilada. So we can't neglect one over the other. Therefore, that particular equation is written like this. Okay. We are going to keep the first power of the V infinity over V infinity, because 1 minus m infinity squared itself is small. So we can't favorites with one small number, keep it, and neglect the other small number. So we keep both of them in our approximation. Very similarly, just as we worked with a squared minus u squared, if you go through the motion a squared minus v squared, you'll get just an a infinity squared. So you have an a infinity squared out here. Here you have an a infinity squared out here. So a infinity squared will drop out everywhere. A squared minus u squared, this part will survive, which is what I have written in here. By the way, I have Vx over V infinity. It should be a Vx over V infinity. There's a typo here. Vyy, because a infinity squared dropped out, I just have 1. So this is the governing equation that we get. In subsonic flow, this is a large number compared to this disturbance term, so we can neglect it. In supersonic flow, this is a large number compared to this disturbance term, so we can neglect it. So in subsonic flow and supersonic flow, we get a nice linear equation. So now we are back in business. Linear equations we can work with. nonlinear equations, you had to go to computer. That's why this could not be solved till 1971 by Merman and Cole, transonic flow. But as soon as they solved it, Jamison solved it for thick aerofoils. Then Boeing came up with their aerofoil designs, 7X7, 737, 747. All these aerofoils were being designed in the 1970s, and they started flying in 1980s, maybe late 1990s. So it takes several decades of development, but the ground was laid in 1971. But for First World War, Second World War, the ground was laid by Prandtl, not for First World War, for Second World War, and Glover. So they worked with this linearized form of the governing equation, which is good for subsonic flow and transonic flow. Now we need an expression for pressure. We know the conventional expression for pressure is P over P infinity, which is the gauge pressure, P minus P infinity, which is the gauge pressure, divided by 1/2 rho P infinity squared, which is the dynamic pressure. If I divide both the numerator and denominator by P infinity, this will become P over P infinity. This will become 1. So that's what we'll get in the denominator. You'll get a rho infinity in the denominator, by P infinity in the denominator. Express P infinity in terms of rho infinity or T infinity. So rho infinity will cancel out. Replace RT infinity as gamma RT infinity over gamma. Then you will pick up Mach number. So this is an expression for CP. Pressure ratio minus 1 by gamma over 2 m infinity squared. Now we are going to replace this pressure ratio by temperature ratio because it's an isentropic potential flow. Then we are going to replace the temperature ratio with this expression that I asked you to derive. Okay. So that's what we are going to do. So CP becomes, pressure ratio becomes temperature ratio. Then this is the expression for pressure ratio. Then replacing the temperature ratio with that equation that I asked you to derive, you get this equation. So CP is still nonlinear because you have a square of terms in here raised to some nonlinear power. So it's still a mess. Okay. So we need to linearize it before we could use it with Prandtl and Glover's theory and Gothar's work, Acker's work, all the things we talked about in the previous video. So again, we replace u and v by v infinity plus vx is u. V we replace by vy. We immediately see that vy squared by v infinity squared can be neglected. When you expand this, you get to v infinity squared by v infinity squared that produces 1. 1 minus 1 goes away. Then you get 2 times v infinity times vx over v infinity squared. That becomes 2 times vx over v infinity. There's a minus sign here that I have carried forth. So now I have an expression here. Although this term is linear in phi, it's still raised to some nonlinear power. So it's not a fully linearized. Then we go to a theorem called Binomial Theorem. This is what the banks use. They give you 1% of interest per year. So 0.01 percentage. So not even 1%, 0.01% these days. Let's say it's a 1% interest. So 1 plus 0.01 raised to the power 10 is approximately just 1 plus 0.1. Okay. So it's a binomial expansion. So whenever we have a 1 plus a small number raised to a power, we could approximate it this way. Since we have this small number, which is a small number raised to the power, we can use a binomial theorem, so we can multiply gamma over gamma minus 1 times this small number. So when you do that, this gamma minus 1 will over cancel out. You do have a minus. Then you'll get 1 minus gamma over 2 m infinity squared vx minus 1. 1 and 1 will cancel out. M infinity squared will cancel out. Gamma will cancel out. So you get a linearized expression for CP, very similar to what you would have gotten in incompressible flow. So we have a linearized governing equations, which we are happy about. Now we have a linearized pressure coefficient, which we are also happy about. So now the third thing we have to linearize is the boundary condition. Then we will take a break, then continue with our next video. So let's take a look at the boundary condition. We'll stick with 2D aerofoil. So the body is a shape, a general shape of the function of the form y equal to some given function, capital Y of x. Capital Y, this may be NACA 0012, it could be NACA 23012, or it could be a supercritical aerofoil. But we do know that the flow has to be tangent to the surface. Flow cannot cross the boundary. That means there can be no normal velocity because it's a solid. So the slope of the streamline should equal the body slope. Now this is my x component of the velocity, which is u. This is the y component of velocity, which is v. Therefore v over u should equal the body slope. Flow slope equals the body slope. Now v is d phi dy. U is free stream velocity plus disturbance velocity. Now I can bring this v infinity plus vx to the other side. Then I take a v infinity out of it. Then I get 1 plus a disturbance, which is a small number, times another small number. Why do I call this a small number? Because mild camber, small angle of attack, thin aerofoil. That means the slope is going to be like 10% thick, 12% thick aerofoil. So the slope is going to be like 0.1. These disturbances are going to be of the order of 0.1 times v infinity. Therefore, this is also of 0.1. So 0.1 times 0.1 is small compared to 1 times 0.1. So I keep this 1, but I'm going to discard this v infinity times vx over v infinity. Therefore, the linearized governing equation is this equation. So now we have a linearized governing equation, a linearized expression for CP, linearized expression for boundary layer. What do we mean by linearization? Phi does not appear as a product of another unknown. Phi does not appear as a product of another unknown. This is a constant. These are all constants. This is a constant, this is a constant. So phi does not have any non-linearity. So Prandtl from Germany, 1922, Glovert in England, 1928, were trying to solve this for two-dimensional subsonic flow. Eckert in Germany in 1928 was trying to solve this equation for two-dimensional supersonic flow. Gothard in Germany tried to solve this for three-dimensional supersonic flows. For three dimension, you pick up an extra term, which is phi zz. That's the only big difference. So we are going to take a break here. We have developed this equation. So now we are going to look at what did Prandtl do. That will be our next step.